Let's be a little bit more precise about orientation. Orientation means the direction we go around a curve. So Green's theorem tells us that we should do a line integral to a double integral. We have to, when we do that, we have to remember that the curve should be going counterclockwise, quote unquote, around the boundary of the region. But counterclockwise is a kind of ambiguous term, and let's see a little bit about what that actually means. Here are three examples of regions inside three-dimensional space. Each of them, we can imagine what it means to go around the boundary of that region counterclockwise. And if we think about that for a second, we might arrive at this description or we might not, depending on how we think about it. So for the region on the left, it's a circle, and counterclockwise isn't really ambiguous. We know how to go counterclockwise around a circular region. For the region in the middle, the boundary is broken up into straight lines. It doesn't really make sense to talk about whether we're turning clockwise or counterclockwise on a straight line, but we want to have those all oriented in the same direction so that at the end of the day, we feel like we've gone around the region in one direction in a net counterclockwise way. And for this region in the middle, if we go around the outside boundary, we're actually going counterclockwise. And if we go along the inside boundary, technically speaking, we're actually going in a clockwise rotation around a circle. But if we're going to be going in the same direction all the way around the curve, we have to make sense of what it means for the net orientation to be counterclockwise. So let's stop foofing around and let's talk about what counterclockwise actually means. It means that if we have some region inside two-dimensional space, we imagine ourselves standing on it and walking on it like so. And the way we should walk around it is the following. We imagine that our foot, our left foot, should be on the inside of the region. We keep walking around this way so that the region stays on our left and the outside of the region is on the other side. So if we're walking around with this region on our left, we should always be walking around this direction. And this is not ambiguous anymore. There's no confusion about which counts as clockwise and which counts as counterclockwise. Now, there are a bunch of really silly memory aids that go along with this. So the ones that I've heard include things like if the region is a pond, your left foot should be getting wet, or some memory aid that I was told in undergrad that had something to do with being on a golf course and carrying a putter, but I don't really understand who that one was supposed to help, and I can't remember it anyway. The main point is you have to remember the region stays on your left, 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 left. It's sided. You have to remember which side it goes on. All right. So also, this helps us in trickier cases because Green's theorem is actually okay if the boundary comes in multiple pieces. Here is a region, kind of a region that looks like a washer, where it has an inside, the inside of this kind of donut-shaped region and the outside of it. Here, the outside boundary has two pieces. There's an outmost boundary that goes around this way, and there's an inner boundary that goes around like this. To orient the boundary properly so that we can apply Green's theorem, we should orient the boundary so that this one, when we walk around it, the region stays on our left. And this one, to walk around this one and keep the region on our left, we should go around kind of the opposite direction. We should go around the opposite direction so that it looks kind of clockwise instead. But both of those are set up so that the region stays on our left when we actually do our walking. And that's how we can remember how this goes.